Hello everyone, this is Dr. Yan. I'm chemistry professor at Eastern New Mexico University, ENMU. I hope your summer is going well. I also hope you like our new initiative this year, ENMU Grades. Funded by National Science Foundation, New Mexico experimental program to stimulate competitive research and ENMU. We've been cultivating algae during the past 6 years in dairy manure effluents on an outdoor pallet scale algal turf scrubber, for short ATS. Our project goal has twofold. On one hand, we adapt algae cultivation to our local conditions, including weather and wastewater characteristics. This is for exploring the optimum conditions for ultimate mass production of biomass feedstock in the semi-arid Southwest. On the other, we try to use algae technology to purify dairy wastewater. This is for creating a closed regional system of wastewater treatment and reuse in local dairies, which helps grow the rural economy. That being said, our project is at the nexus of energy, water, and the environment. It's under the National Science Foundation's Growing Convergent Science. In the next 40 minutes or so, I will talk about the importance of algae, algal research, the existing challenges facing the algal community, and provide a snapshot of what we have been doing during the past 6 years. This figure shows us the world's population size and annual growth rate over 1.5 centuries. The world population continues to grow, albeit the slower pace than at any time since the 1950s. The current population of 7.7 billion people pushes our current food production system to its limit, leading to a global food and nutrition crisis. Here are some facts from the Food and Agriculture Organization of the United Nations. The highest burden of hunger exists in South Asia, especially in India, where over 281 million individuals suffer from inadequate diets. Meanwhile, some 100 million children worldwide are underweight, and almost 10 million children die every year due to complications related to malnutrition. Poor nutrition plagues the developed countries as well. About 1.5 billion adults around the world are either obese or overweight and at risk of non-communicable disease. Micronutrient malnutrition, the so-called hidden hunger, is the closest thing to a global pandemic. The coronavirus crisis has shown us how vulnerable we all are and how important for us to restore the balance between human activity and nature. Although effective treatments are elusive, scientists, healthcare workers, public health professionals are making good progress toward developing a coronavirus vaccine. We all hope that can happen soon. By 2050, another 2 billion new guests will join the world dinner table. It has become more and more urgent to find a sustainable, resilient solution for global food shortage and chronic malnutrition. Biomass can be grown in a productive, profitable, and environmentally sustainable manner to address the growing demand of food, feed, fiber, and fuel. Bioeconomy industry harnesses the domestically grown biomass to enhance the nation's security, economic growth, job creation, and environmental quality. In 2000, the Biomass Research and Development Act was enacted. The Biomass R&D Board and a Technical Advisory Committee were established. The board facilitates coordination among federal government agencies that affect the research, development, and deployment of biofuels, bioproducts, and biopower. The membership consists of U.S. Department of Energy, U.S. Department of Agriculture, and 6 more executive branch agencies. Very recently, the European Union has published European Green Deal. The farm to fork strategy is at the heart of the Green Deal. It addresses the challenge of a sustainable food system and links inextricable link between healthy people, healthy society, and a healthy planet. Algae is the mother of all plants and the Earth's original superfood. Relative to surface area, algae yield 5 to 10 times more than conventional terrestrial plants do. Algae release almost 50% of all atmospheric oxygen, which we cannot live without it. Clean energy can be produced from algal biomass in simple chemical processes. Algal biomass can also be used for animal feed, nutritious supplement for human health, and cosmetically, pharmaceutically valuable materials. And finally, algae thrive in municipal sewage, animal waste, and some industrial wastewaters. They purify this wastewater while producing biomass suitable for biofuel production. This is a beautiful cartoon. This cartoon compares freshwater footprints and land productivity for representative elite algal strain nanoclarvices, for short nano. With other food production systems, for instance, from beef to seabrain to peas to pork, chicken, and soybeans. Be brief. Nano consumes the least volume of fresh water per kilogram of essential amino acids. As we see, that's 20 liters of fresh water per kilogram of essential amino acids. as a comparison, we see it takes 140,000 liters of fresh water for per kilogram essential amino acids from beef. Well, Nano yields the highest land productivity. You see here around 6,100 kilograms of essential amino acids per hectare, relative to only 22 kilogram essential amino acids per hectare from peas. This slide is taken from NREL's Billion Time Report in 2016, NREL National Renewable Energy Laboratory. And this table here listed the season-based algal productivity. Obviously, we see summertime, the productivity reached the peak. Well, wintertime, it reached the valley. On average, for the 4 seasons, the annual average productivity is 25 grams ash-free dry weight per square meter per day. And this table also tells us the evaporation loss of water. You see here, springtime, the water evaporation loss was highest. I think we all know the reason, because of the wind. On average, for the 4 seasons, we have about 0.087 centimeter per day water loss. And of course, this is for the open pond cultivation or operation. And DOE set a goal for productivity by 2022, which literally about 2 years later, we would like to have the annual average of 25 grams ash-free dry weight per square meter per day for the productivity. So far, the highest reported productivity is around 23.0 grams, and 8 to 21 grams usually from April to October. And we know summertime reaches the peak, wintertime reaches the valley. We would like to have the maximum versus minimum productivity ratio to be about 3 to 1. This is a very busy slide. It was taken from National Algal Biofuels Technology Review in 2016. And particularly, this slide summarizes algal feedstocks R&D technical challenges and existing barriers. It from 3 perspectives, namely algal biology, algal cultivation, and harvesting dewatering. I would like to bring your attention to 2 points on this table. And particularly, we would like to look at open pond housing operations. And particularly, we think about involving ecology, predators, and pond crashing. And in terms of algal cultivation, I would like to bring your attention to managing resources in a cost-effective and sustainable manner. When I say resources, I pretty much refer to water, nutrient conservation, and recycle. As you know, when we try to harvest algae, we need to have energy-saving techniques. And currently, for dewatering and drying, takes too much energy. How we can minimize the energy consumption would be critical in our effort to convert algal biomass into biodiesel. This is a map for our state, land of enchantment. And New Mexico has about 150 dairies. And New Mexico has the largest average herd size of 2,088 cows in the nation. Currently, New Mexico is ranked 9th for milk production and feeds for cheese production nationwide. More than 75% of milk volume is from east side of the state, where the main campus of Eastern New Mexico University is located. To give you some quantitative idea for the amount of manure generated in the industrialized dairies in New Mexico, on a single day, 5.6 million gallons manure. Only 1/3 of New Mexico dairies, however, pass the state groundwater standard for nitrate. The biggest cheese plant, Southwest Cheese, LLC, is also located about 15 miles to the main campus. On a single day, Southwest Cheese produces 1.2 million gallons of cheese whey wastewater. The readily accessible bulky wastewater makes ENMU a natural research site to study how to turn wastewater into green energy and high-value products in a cost-effective, environmentally sustainable manner. This slide summarizes nutrient flow for dairy farm operation. As you see, about 1/4 of nitrogen phosphorus reach our milk. The rest, about 70% nitrogen phosphorus present in raw manure. If you ever visit a dairy farm, you'll see a solid liquid separator just in front of the lagoon. So after solid liquid separation, we have about 50% nitrogen phosphorus present in manure effluent. As I mentioned, traditional dairy wastewater treatment often relies on anaerobic lagoon. The lagoon is not high-quality wastewater treatment, but rather limit runoff into surface water. Developed in early 1980s, ATS is a solar-driven system that produces algal feedstock while simultaneously removing nutrients in wastewater and impaired waters as well. Shown here is a laboratory scale ATS system. Be brief. There's a drum containing fresh water. Dairy manure is loaded on a daily basis. The resulting scrubber effluent is continuously recycled to the system using a sump pump. On top, there's a trough. It fills, tips over, releasing pulses of effluent that wash over the attached turf before draining back into the ground. Utilizing surging motion of effluent breaks down the diffusion boundaries and increase nutrient uptake. Here's a picture for the ATS system. It's from the commercial vendor called Hydromancer, which we have partnered with. In terms of ATS, it has many advantages. For example, it's a polyculture. You will never worry about the productivity. Remember, the DOE goal by 2022, 25 gram ash-free dry weight per square meter per day. It does not require nutrients or CO2. We use the CO2 from the atmosphere. And in terms of harvesting and dewatering, it's very simple and straightforward, which I'll show you what we do. And it has very low operation cost. as any technology, ATS does have its downside. For example, it has very high ash content, either biotic or abiotic. It also subject to unpredictable, uncontrollable meteorological conditions. But you know, ATS is a potentially cost-effective technology for wastewater treatment and for sustainable biofuel production. There's a picture for our carbon recovery unit. It's pretty sizable, 120 by 80 square feet. In terms of depth, it's about 2 feet deep. And this picture shows you our flowway. It's 100 feet long, 1 foot wide. And we also have flow meter, which allow us to precisely control the pumping rate of the effluent. And you see here the sign filtrator, very similar to our residential swimming pool. It helps us filter off some windborne debris. And this picture shows you how we harvest the algae. As I mentioned, very simple, just mechanical scraping. And after we remove predators' debris, we'll bring them into the laboratory to rinse with distilled water. And then we'll do centrifugation and air drying and oven drying. This picture shows you how the dried algal biomass looks like. In our early days of operation, we saw single-cell phytoplankton, microalgae on our flowway. This table here shows you location-dependent concentration for several representative microalgae species. For instance, 30 feet from the beginning, 90 feet from beginning, which means towards to the end. And in terms of the species concentration, we'll see Synecdasmers, Cosmerium, Navicula, Naskia. They have relatively high concentration down the flowway. We did not see filamentous algae for productivity enhancement. It would be really nice to have macroalgae, the filamentous one. And I'm a chemist. Let me show you some chemical reactions. And this is a triglyceride. This is alcohol with 2 carbons, we say ethanol. When they react with some catalyst, either acid or base, we will create this fatty acid, acyl ester. Guess what? This is the biofuel. It's not that viscous as compared to triglyceride. It's matchable with our current thermal engine for our vehicles. So that means, this very simple chemical reaction, in technical term, transesterification, we can produce biodiesel. And for this biodiesel, we would like to know the formats, the components. Let me tell you one laboratory techniques we have here at Eastern New Mexico University. Gas chromatography, which is basically a separation technique. Using this technique, we are able to see the various components of fatty gas and acyl ester for short fins. For instance, they have even number of carbons, like 14, 16, 18, and somewhere you see here 20, and even 24. And I really want to mention this. When we look at this omega-6 and omega-3, They are omega-3, omega-6 unsaturated fatty acids. Guess what? We need them in our body, but we cannot make them by ourselves. That means we got to have these ingredients in our food. This gave us a wonderful idea about the value and usage of algae. And also, for another example, you may have heard, omega-3 fatty acids for, nutritional supplements. And some of them actually derived from algae. And this figure here shows you our productivity. Of course, you see the highest achievable is around 5 grams ash-free dry per square meter per day. We're very far from the 25 target. And when we look at the ash content, it's pretty high. On average, I would say somewhere about 55%. When we look at the biodiesel production, very low, about 0.5%. When we analyze the carbohydrates, it's a single-digit percentage as well. We also try to use what's called pressure cooker way to squeeze out the oil. That's talk about thermal hydroliquefaction, THL. And when we look at the percentage for biofuel yield, it's very low, generally speaking, around 3%. Why we have this? What's the inherent reason? Well, we look at the pH of our effluent, and we also look at whether or not we have enough carbon sources in our effluent. And turns out we do not have much of those in our effluent in our early days operation. Shown here, that's the hourly pH data for a period of 4 months. You see, we could have the pH reach about 10. We could have low pH around 7. And when we analyze this bulky data, we see the average pH is actually around 9, a little high. What do we thought about? Let's try to introduce flow aqua plants into our carbon recovery unit. Let's also try to use shade cloths to cover part of our carbon recovery unit. You see the shade cloths here, they can reduce 70% sunlight and block up to 90% ultraviolet. And because of this, we see a significant change in the pH and temperature of our effluent. And if I show you that data, here's a picture, show you the happy duckweeds and the happy cattail. When you have such a dense layer of floating aqua plants, you block sunlight, you block UV. You also introduce some organic carbon. As a result, when we look at this figure here, left y-axis tell you the pH, right tell you the temperature. You see the highest pH is around 8, the lowest around 7, and the average, I would say, around 7.4 is pretty near neutral. And when we look at the temperature even across the 3 months of operation, from a really hot June to somewhere the end of October, and we will see the average temperature is around 20 degrees Celsius. From this very simple introduction of floating aqua plants and covering the pond with shade cloths. And this is a close-up for the filamentous algae on the flowway. We did strain identification or taxonomy analysis. We noticed that's actually Rhizoclonia species. And this picture shows you the harvested wet biomass. When we did air dry, this shows you air dry biomass. Productivity matters. When we really look at our productivity data, we're pretty happy about it. You see the highest achievable here is around 16 grams ash-free dry weight per square meter per day. We also see significantly lower ash content. Remember, in our early days operation, we have average ash content about 50%. Right now, you see we can lower that to about 24%. When we did film analysis, you see increase from about 0.4% from early days operation to the data here about 6%. When we look at the carbohydrates, it increased significantly. Even more interesting, when we use T12, try to squeeze the bio oil, we see that go up significantly to about 14%. This is done through collaboration with New Mexico State University. And we also try to monitor nutrient removal. On this slide, I should give you some idea about phosphorus removal. Shown in the left figure here, somehow give us baseline information. During this 1 week monitoring period, we see average phosphorus content in our effluent, I should say, is about 0.32 milligram per liter. And for the next 3.5 days, we load nutrient into our carbon recovery unit and monitor the phosphorus removal. And we have this beautiful data showing in this figure. When we did data simulation, we can have this fitted line equation, which tells us per hour we can remove about 9 microgram per liter phosphorus. And this data is very comparable to the phosphorus removal rate in literature. And to get this data, we count on our industrial standard spectrophotometer. You see, this is the benchmark of the industry for water testing, wastewater characterization, and nutrient removal. All this data were collected in our own research laboratories. On this slide, I try to give you some idea about nitrogen removal. And a little complicated, and you see here, we have 3 different symbols. The solid square, black, represent total nitrogen. The green triangle simplified total colloidal nitrogen, for short STKN, and the solid red dot represent the sum of nitrate, nitrogen, nitrite, nitrogen. This is the baseline data over 1 week monitoring, and this one shows 3.5 days nitrogen removal rate. And you see, we have linear nitrogen removal tendency. And when we do the data feeding for STKN, the data here tells us per hour, per liter, we can remove somewhere about 40 micrograms of nitrogen. We have this question. We see advanced nutrient removal. We see significantly improved productivity. What causes this? course, another chemistry-specific equation tells us the process for photosynthesis. We gotta have light. We gotta have appropriate pH. We gotta have right temperature. If you remember, after introducing flow aquaplants and sheet pond with sheet class, we reach these conditions. Now, we got to think about the attached algae bacteria consortium. For the consortium, there exist cooperative, competitive interactions. In the cooperative interactions, algae provide organic carbon, oxygen to bacteria. Bacteria provide CO2, nitrogen, phosphorus, vitamins, oxygens, minerals to microalgae, thus promoting the growth of both algae and bacteria. Or we should say, this cooperative interaction is symbiosis. While in the competitive interaction, or what's so called antagonistic interactions, microalgae produce antibacterial substances to inhibit bacterial growth and to inhibit quorum sensing of bacteria. Simultaneously, bacteria produces antibiotics to interfere photosynthesis or to produce algae-side metabolites to inhibit algal growth. And it seems our advanced nutrient removal and improved productivity is from symbiosis process or cooperative interactions. To prove this, we collect fresh sample overnight to our collaborators in Los Alamos National Laboratory for bioinformatics or microbial analysis. And overnight, our sample to Arizona State University for algal strain identification, or in technical term, taxonomic analysis. On this slide, you'll see the metagenomic analysis data. And this red color shows what happened at the end of the flow, while blue area shows that at the very beginning of the flow, 20 feet. Yes, we do not have a simple system. It's way complicated. And shown on this slide, all these species have more than 100 contacts in the NCBI database. I really want to mention this. At the very beginning and end of the flowway, we have very high abundances of Aeromonas species, which indicated here by this symbol. And this slide shows OTS counts at the very beginning and the end of the flowway. And when you see letter G here, that represent genus level. Well, F, family, O, order level. And I really want to talk about two bacterial species, shown here, Cytophagesi, and shown here, Rhodococcus fasciens. The reason I want to mention these two, because you see, we only see that show up at the end of flow. They do not present at all at the very beginning of the flow. On this slide, we have the most abundant genera associated with conifers at 20 feet down. And I really want to mention this species. you see it only show up at the beginning of the flow, not the end. And these species involved in sulfur metabolism. Well, other overrepresented species also labeled here, for example, Hafnia, high amount at the very beginning, relatively high amount at end as well. Same thing happened for this species, Sinansi virga, and this species as well, Algae vector. This slide shows you the contours at 80 feet down the flowway. And for this species, Citrobacteria, it's very important because this species converts nitrate to nitrite. It's nitrogen reduction process. And I also want to mention this unique species as well, Nitrosomonas. You see, it has really high presence at the end, but very low amount at the very beginning. And Nitrosomonas converts ammonia into nitrite. You know, for our manual effluents, it's really high content ammonia. And this species can do the conversion from ammonia to nitrite. And we have other species which are overrepresented as well. Really Rhizobium, and shown here, and Azospirillum, and Conexibacter, somewhere shown up there, and not show up at the very beginning, but show up relatively high toward the end of the flow. And in terms of the strain identification, taxonomic results shown here for our sample collected in July 2017, we see these two green filamentous algal species, namely Stagiocolonium and Cladophora. And very interesting, when you look at their population data, you see at 20-40 feet down the flowway, these two filamentous algal species, they have about 50% presence. Further down to the flowway, Stagiocolonium reached somewhere about 90%, while Cladophora dropped to only about 10%. We also have relatively high presence of diatom. Microalgae, it has a very unique name, Gomphonemon. And we see down the flowway exhibit linear drop from 4% to 1%. And at the same time, we sent sample to Lano for another bioinformatic study. And shown up here, we have the phylogenetic correlation for the major species identified. And in terms of their quantitation, we have this figure here, and from this figure, it's quite evident. We have several species, they drop significantly down the flow. For instance, Formidium and Pseudonaceae, very difficult to pronounce, and also Chromataceae, and shown by this line, that data. This is really important species because it involves sulfur metabolism. And when we look at the bacterial community down the flowway, and particularly, and at least tenfold higher representation toward the end of the flowway, we see this population variation trend, and seems like Bacteroidetes and Bacteroideaceae, Burkholderia, and they have increasing population, and with their phylogenetic information here. In addition to outdoor laboratory facilities, in my research laboratory, we also have this commercialized indoor bioprocess control station. This is the cultivation chamber, this is the controller, and this is a light module. This allows us to manipulate the outdoor environment so that we can explore the optimum condition in an indoor setting and then amplify that in our outdoor system. And of course, some of you may say, hey, the indoor condition may not be the same for outdoor. Yes, we are trying to prove this. In addition to photobioreactor, we also have this so-called airlift photobioreactor. You see different tubes. This is before the inoculation. This happens when we harvest the algae. This work is in collaboration with the University of New Mexico. Let me give a brief wrapping up. Controllable pH and symbiosis of microbial communities have enhanced algal biomass productivity. Somehow also improved nutrient removal rate. The ATS flowway appears to be a highly dynamic ecosystem. At the very beginning, sulfur metabolism predominant, gradually converted to nitrogen-based metabolism at the end. One thing I really want to mention here, controlling algal-bacteria consortium and systems performance needs teamwork. We need people from biotech, ecology, genetic environmental engineering, and even mathematics, because they do modeling which guide us for real laboratory work. I'm grateful for the help from my collaborators, my partners, and my students, both master level graduate students and undergraduate students. Thank you all for your kind attention. I know this is the end of my talk. There's one thing I'd like to share with you. Eastern New Mexico University is a great institution. Why I say so? Well, 18 years ago, when I came here, I had an intent to stay here for 2 to 3 years, earning some teaching experience, then move to big RY institutions. Guess what? That did not happen and will probably not happen in the future. This is because of the institutional mission and our culture. Student success, that's all what is about. And if you're interested in the research we do, if you want to get more information for this great institution, please contact us. You all are welcome to join us as Greyhound. Go Greyhounds! Thank you.